So we will do section 9.2, which is convergence for strongly convex and bounded gradients. So this is theorem 9.8, and we assume stochastic convex and G bounded. And we assume that F is mu strongly convex, and we consider the sequence xt generated by SSD, the stochastic subgradient method that we are doing, and with the constant step size. So in this case we say constant step size, which is gamma t is said to be gamma, and that lies between open 1 by mu. Okay, so then this result says that expectation of xt minus x star is less than equal to 1 minus gamma mu x naught minus x star whole square plus gamma g square by mu. So this is not bound on the function values. As you can see, this is bound on this iterates itself. Okay, so this is how the difference between the the difference of the xt from x star is compared to x naught and x star. X naught is the starting iterate value. So to prove this, we start from the left hand side, which is this expectation. So we will basically expand this. So if we expand this, first of all, xt plus 1 is follows the SSD iteration. So we will write xt plus 1 as xt plus minus subgradient times that's it. So step length times subgradient. So that's what we are going to do. So this is xt plus 1 is xt minus, and subgradient in this case notation we will use is g xt jt, and the step length we are using is gamma. Okay, and then this is minus x star. Okay, and then we will again split this into a minus b form. So this is our a and this is our b. Okay, so this is xt minus x star squared plus gamma square norm of g xt jt squared minus 2 xt minus x star gamma g xt jt. Okay, so we have expanded this. Okay, so some of the assumptions we have used we have already given, like bounded, so we can clearly use this for the second term, that the subgradients are known to be bounded, so that will be less than equal to capital G. And for the third one, we know that those kind of terms where these things are used, mu strongly convex and all these are used to bound the inner products. So that's what we are going to do. So so the facts that we will use are subgradients are bounded, are G bounded. So if we have to do this step by step, then with this fact I can write this as xt minus x star, and then with this I will have this, I will leave this second term for the moment, and it's bounded but when I mean in the expectation, right? So first step will be the apply the expectation first, and then so let us, that step we have to do first. Take the expectation with respect to xt. So taking expectation expectation with respect to like conditioned on xt basically. Okay, these are the usual steps we do, conditioned. So we do that, then the first term we won't have the expectation applied, it's no longer random. So then, but this guy will be, because gradient is being computed at xt, so that process will generate a random variable. And so so what we'll do is, an expectation will indeed apply on the left hand side, which is this guy. Okay, so we are taking expectation of both sides. So this is expectation of x t plus 1 minus. So xt plus 1 is generated from xt via gradient, and this is a random variable. So xt plus 1 remains a random variable, and this is equal to norm of xt minus x star whole squared plus, and expectation will apply here. So this is gamma squared expectation of norm of g xt xi t norm squared, and then minus 2, and expectation will apply only on the second term there. So this is xt minus x star expectation of gamma, we can take it out, and this is g xt xi t. Given subgradients are bounded, so this immediately implies that our left hand side, so in this case we copy it again, xt plus 1 minus x star whole square, and all this is conditioned on xt, and this is less than equal to x star So the last term denotes that that bound. So that's the first step, and then the second step will be the mu convex term. Okay, and in fact this will be the subdifferential of f. So it's a subdifferential of f, and then f is mu strongly convex. Okay. So then if f is mu strongly convex with the subdifferential of f, inner product with this satisfies that mu strongly convex inequality, right? So this two-step thing will be needed here. So using this, so basically we can copy over this lemma basically. So these are the two lemmas that we use. So since we are recording, maybe it's good to copy over a little bit. So this was the lemma that says that expectation of g x xi is a subdifferential of fx. So this already we proved it. And then what we will need more is the mu strongly convex definition as well. So mu strongly convex was lemma 8.14, and that says basically, I mean lemma 8.12 in the notes. So that says f from Rd to R mu strongly convex. So it's like proper LSC and mu strongly convex. Then what it satisfies is this fy minus fx minus eta y minus x is greater than equal to mu by 2 norm of y minus x whole squared. So this is the mu strongly convex definition that we are going to apply, and we will apply this on this because this is the inner product we have in mind, which for this is the inner product we are looking at. So as I said, this is a two-step process. First step process is that this qualifies as the subgradient of f. So this guy qualifies as the subgradient of f. So then if it is a subgradient of f, then for that where eta is a subgradient of f, this inequality satisfies, right? So this is what we will do, right? So if we solve for this inequality, then we move this, which we choose proper y and x basically. So basically we solve for this inequality, then if and set proper choices of x and y. So this inequality tells us, especially for the inner product, and there is a negative here, and what we are looking to bound is also negative, so we can keep the negative term here, and then this is eta y minus x, and this is greater than equal to mu by 2 norm of y minus x whole squared, and then minus fy plus fx. Okay, so we have to squint, right? There's an English word squint at this, and see what could be a good fit for xt and x star. So y minus x, the gradient is computed at xt, so that gives us a hint that eta is corresponds to that, but then yeah, so basically y will be xt. Okay, I'm a little bit confused. Yeah, so y will be xt. No, I think x will be xt. Yeah, it seems like we have this in a, because obviously you will compute a gradient on something that varies, right? You won't compute it at x star. So what it seems is that the gradient is computed at xt, but then this is written in a different way. So what we have to do is, like, we have to let us we can observe this and we will see this later. So this is x minus y, and gradient is being computed at, so xt is my x and y is my x star. Okay, so with this xt is x and y is x star. Okay, so I believe this should be a good choice. So with this, then what will be this? Okay, with this choice of eta is our this, right? So we can try to do this, right? So this is ed of g xt xi t given xt and xt minus x star, and this is greater than equal to, with our choice, right? So this is greater than equal to, and this is mu by 2, and y is our x star, x is xt minus fy is our x star, and x is xt. However, everything was in f, right? Okay, so let us see that these were the same f we were using. Yeah, so these are the same f. So but then what we want, we are looking at the upper bounds of these, right? So so we take a negative of this, and then we get the upper bound on those, and there we have to take the negative. So if we do a negative of this guy, and with also we can put the gamma and all. Okay, so negative, then this becomes less than equal to 0, I mean less than equal to sign, and this becomes negative, and this becomes positive, and this becomes negative. So and then we have to multiply with the 2 gamma, and so let us do that as an additional step. So everywhere there will be 2 gamma. So everywhere I have multiplied with the 2 gamma. Okay, so this is the workspace we used, and now we will continue from here. Okay, so now we continue from here. So we basically do this upper bound. So we have not, okay, this is the last term. I was thinking where is the, there should be 3 terms there. Okay, so we have further upper bound, and xt minus x star whole square minus, now this we have this, right? And there was a minus also. That's how the inequality got changed. So then we pick the right hand side, which the 2 gets cancelled, so it's minus mu gamma. Okay, so this is minus, okay, then yeah, the whole minus is less, so okay, that's fine, so it remains minus mu gamma, and then norm of x star minus xt whole squared, and then plus 2 gamma fx star minus fxt. Okay, so let's check. So this is xt minus x star whole square, and then minus to gamma, then this is minus mu gamma x star minus xt, and then to gamma f x star minus f xt. Let me check in the notes also. So okay, so yeah, I mean, they have changed this with a minus there, but it's fine, it's the same thing, minus mu, and then right, and then we have this remaining term plus gamma squared g squared. So then it seems like something is can be taken common, like these guys are common, so we can take that, and we don't do any further. Oh, we also drop. Okay, so basically we can drop this guy. So it's the idea is that this guy is what? This guy is, so this is the infimum, right? And this is some value. So infimum is supposed to be always lower, right? So this guy is certainly going to be negative, right? So if I drop this guy, still I get an upper bound. Okay, so this guy is supposed to be less than equal to 0, and gamma is positive, so this guy is less than equal to 0. So if I drop this, I still get an upper bound. So we can write this here in the notes, okay? Because usually sometimes we forget. Okay, so this, I mean, in this case it's hard to forget. There's a video also. So here fx star minus fxt is less than equal to 0, so we can drop this. So this is the thing we will do. We will take common and we will drop that, and hence we continue to have this less than equal to sign, and this is 1 minus mu gamma norm of xt minus x star whole squared, and then we have just the last term, which is gamma squared g squared. Okay, so what we'll do is that we will take expectation and then use the recursion. So the recursion is now left hand side is here, so t plus 1 x star is now in the form of t x star. So this is a clear recursion that I will again use this. Using this, I will again expand this, so then I will have 1 minus mu squared and xt minus 1 minus x star and so on. Okay, and then this guy will also apply to this. Okay, so due to recursion, then we will now go until the boundary, which is x naught. I mean, so we are taking expectation and using the recursion. Using recursion, we deduce that expectation of xt minus x star 1 minus gamma mu t norm of x naught minus x star whole square plus 1 minus gamma mu t gamma squared g squared k equals 0 to t minus 1. Okay, so this is a simple exercise to check that due to recursion this is what we will get, and so we will look to simplify the last term, which is sum of so basically it seems to be like the geometric sum, right? So we'll use that. So the last term is k 0 to t minus 1 minus gamma mu t gamma squared g squared is gamma squared g squared 1 minus gamma mu t by gamma mu, and this is less than equal to, so apparently this the 1 minus gamma mu t is less than equal to 1. Okay, is less than equal to 1, so we may have to look into what was given, right? So gamma mu, okay, yeah, so gamma mu is between open 0 1, right? So that's what we are going to use. So if you may recall, so here itself I can write, so here we can write that because gamma was in the interval 0 1 by mu, so this implies that mu gamma must be in 0 1. So with this we will make this less than equal to 1. Okay, so this is less than equal to 1, so 1 minus something less than equal to 1 is less than equal to 1. So hence we can simplify this to gamma g squared by mu, right? So gamma g squared by mu. So overall now we can now write the final line, the conclusion, that's exactly what we are supposed to prove. So yeah, exactly, this is exactly the form we had. So this implies that, so we can write this final statement that xt minus x star is less than or equal to 1 minus gamma mu t norm x naught minus x star whole squared plus gamma g squared by mu. Okay, so this is what we were supposed to prove. Yeah, so then we move to 9.3, where we will have some assumptions also on the bounds of the solutions. So all this will be useful. So 9.3 is about better convergence rates for convex functions with bounded solutions. So now we will have bounded solutions also. Okay, so let us see a consequence of that. So what we will assume is 9.9, which says B bounded. So this means that there exists a constant B greater than 0 and a solution x star in argmin f such that norm of x star is less than or equal to B. So basically it says the solutions that I get are bounded. So what could be the consequence of this, right? So if we have that the solutions I'm looking for are bounded, then the iterates I will generate, I will make sure that the iterates also satisfy this. Okay, so basically I will make them project in a ball of radius b. Okay, so then hence we will define a projection. So exploit this by modifying the SSD by adding a projection step. Okay, that's what we are supposed to do, because solutions are supposed to be bounded, adding a projection step. On the closed ball 0b, right? So closed ball b 0b with center 0 and radius b. So this projection operation will be defined like this. So this is projection b 0b of a vector x, and this is x if it's already in the if the norm of the x is already less than or equal to b, then I don't have to do anything. If not, then I will normalize this like this if norm x is greater than b. Okay, so if norm, so as you can see, if norm of this s is greater than b, then if I take a norm of this, then norm gets cancelled and is less than or equal to b. Okay, so then it means that the projected x by this projection is ensured to be in the ball 0b. So then we can define something called projected stochastic gradient descent and see what benefit it gives, right? So then we define an algorithm. This is called PSSD, and that means so consider a stochastic function and let assumptions of those convex and so on hold. Assumptions of stochastic convex and G bounded gradients, in this case subgradients. Okay, so all this holds, and now additionally we are saying that solutions are B bounded, okay, and B bounded solutions, B bounded solutions, and we start this algorithm with an initial iterate x naught. So let x naught be in, I believe, RD, and the sequence of step sizes are taken which are supposed to be greater than 0. Now then we define a projected subgradient method. So then the projected subgradient method so denoted by PSSD is given as follows. So xi t is a random variable because we are always dealing with now random functions. Okay, so we are working on stochastic optimization problems. So this is xt plus 1 is projection 0b and xt minus gamma t g xt xi t. So these guys are sampled IID, independent identically distributed, and these g are the subgradients of f. So where g xt xi t is in the subdifferential of f computed at xt for the stochastic function f xi t. Okay, so each choice of xi t gives me a different stochastic f. It's not the true f. So so for PSSD we will prove a bound. So how it will converge, okay, and with this we will stop for today. So this is theorem 9.11. So assumptions hold, so which is stochastic convex, G bounded, subgradient, and B bounded solutions. Let xt, yeah, we are just writing the same similar stuff. It's just an independent theorem here. So xt be the iterates of PSSD, and in this case we will choose a step length which is decreasing. So let us see that with step sizes gamma t, which is gamma by square root of t plus 1 and gamma greater than 0. Then we have for t greater than equal to 2 and xt bar defined to be 1 by t, xt t equals 0 to t minus 1. So now again we are this convergence result is on the average of the iterates, right? If you can see this analysis that we are doing, either we suit so last iterate convergence or average iterate convergence. Okay, so in convergence analysis these are the two types of things people do, either your last iterate converges or average of the iterate converges, but it doesn't matter. In the average case the only thing is like you have to keep a running average of your solutions, okay, but it also converges, so it's okay, still you have a solution, right? So so then we have ed f x bar t minus infimum of f is less than equal to 1 by square root of t 3b squared by gamma plus gamma g squared. So this is the main result we want to prove. Good thing about average is oscillatory stuff is also kind of implicitly kind of gets cancelled, okay. Last iterate convergence are usually more difficult to prove. Okay, so let us prove this. So we have in this case additionally we have bounded solutions. So solutions are supposed to be bounded, and this will have an implication obviously. So according to our assumptions, since we are in this bounded solution domain, our solution x star must be also bounded. That means that the projection of x star, so which is x star, and then we write here as in the ball 0b will remain x star. Okay, so that's by the assumption that this is a b bounded case, right? So this x star remains x star. So and projection is non-expansive, and this we have such projections are non-expansive, and this we have seen this in lemma 8.16. Okay, so if I have it here, then I will write it. 8.16 is the non-expansive for the, so projection is a proximal operator and proximal operators are non-expansive. Okay, so these are the two facts we recall that we have proved before. So I'll just write this statement so that it remains kind of complete. So we just recall this statement, and this is why we need to use this fact. It's non-expansive. So we recall 8.14. So projection is a proximal operator. So projection is a proximal operator, and we are going into the specifics. And then we had the lemma. So this was lemma 8.14, and this is lemma 8.16, and this was about the non-expansiveness. And this says that proximal g of y minus proximal g of x is less than or equal to norm y minus x. So you just recall this, we have done this proofs. So now we will use this fact to prove this theorem. So going back to the theorem, so let us start with the norm of xt plus 1 minus x star, and we will introduce these projections. So let us do it from here. So we will start from xt plus 1 minus x star, and this we can insert the, since these are non-expansive, so I can write a projection of these guys. So this is projection of b 0b and xt minus gamma t g of xt xi t minus projection of b 0b x star norm squared. So what we have done, since it's a non-expansive operator, just that I have done one more step, that xt plus 1 is xt minus this, and this follows from the PSSD algorithm. And then I can insert the projection operator and it will still not expand. Okay, so that's the non-expansiveness. So then let's see what happens further, right? So this is less than or equal to, now this guy we know, this projection was the x star itself, so I believe that doesn't change. And then so this will be less than or equal to xt minus x star. Yeah, x star is there. So how do we say this? Xt minus x star. Yeah, x star for sure. And then this is minus gamma t and g of xt xi t. Yeah, because the PSSD algorithm will ensure that, right? Yes, it will ensure, right? That's the goal of PSSD, right? So PSSD algorithm will ensure that this remains within the ball, right? That's part of the algorithm. And if I'm doing further projection on that, then if I'm doing further projection on that, then this guy will remain. Okay, I hope I'm not missing anything. I think I'm okay. So PSSD algorithm ensures that the new iterate that I will compute will be in the ball 0b. Okay, so that's already in the ball 0b. So if it's already in the ball 0b, then the projection of that will be the same thing. That's the first point of the projection operator. If it's already there, then so in that case that remains the same. And my x star was already within the ball, so that's already there. So now we will expand this. So this is like a minus b form. So this will be a norm of xt minus x star squared minus, and then we take inner product term, so minus 2, and gamma t we take out, and this is g xt xi t and inner product with xt minus x star plus gamma t squared and norm of g xt xi t. So we have just expanded this. Now we are doing this so many times, now we know the steps. Now we will do expectation, condition on xt. So taking expectation conditioned on t, I mean xt. So we have that expectation of d norm of xt plus 1 minus x star conditioned by xt is equal to xt minus x star whole square minus 2 gamma t expectation of g xt xi t and condition on xt, and then xt minus x star, and then plus gamma t square expectation of D, norm of G xt xi t, condition on xt. Okay, so and this is like norm squared here. So we have taken a condition expectation with respect to xt. We have done this like 4 or 5 times already, and then we do the usual stuff, right? We look for the boundedness of the subgradients. We look for the convexity. So that will be the second term in the inner product will be replaced by that. And boundedness, I think we have already used. So I don't know if we will use further. So that has been already used, that the solutions are bounded. So let's see what we get. So as usual, boundedness of G, and so I will skip those steps that F is convex, and hence we get rid of the inner product also. So by that we will save some time, right? Because we have already done this a couple of times. So what I can write directly now is this. Okay, so here I will write use boundedness of G subgradient, boundedness of subgradient. Okay, so that will make this less than equal to G squared, and then use convexity of F. Okay, so this can be skipped. Okay, I mean you can check this. So this overall, this will be less than equal to norm of xt minus x star whole squared minus 2 gamma t fxt minus fx star plus gamma t squared g squared. Okay, so that's, now we will divide throughout by 1 by gamma t. Remember that the result was on the average, right? So and in the average, yeah, this was a simple average. Okay, just xt sum of xt. Yeah, so we will divide by gamma t first, and since it's over the sum, we will take sum throughout. Okay, these are the 2 steps we are supposed to do. So dividing throughout by gamma t by 2 gamma t. Okay, and then we will like put that fxt minus fx star on the left hand side, because the result is about that. So we do this few things in one shot. So taking expectation, so dividing by gamma 2 by t we already did, and then we also further take expectation and rearranging. So if we do that, then we have fxt minus fx star, and this is less than equal to 1 by 2 gamma t, expectation of xt minus x star minus 1 by 2 gamma t, expectation of d, norm of xt plus 1 minus x star plus gamma t g square by 2. Okay, so this is the simple steps we have done, and then now the next step is that we will sum it. So sum from t equals 0 to t minus 1, and using telescopic cancellations. So if we do that, then we have t equals to 0 to t minus 1, expectation of t, f of xt minus fx star, and this is less than equal to 1 by 2 gamma naught. Okay, so what will happen is that these guys, right, so they are the same, but I mean same in the sense like even the constants are the same. So obviously inner ones will get cancelled. So the last terms will remain with the capital T, and the first term with x0. So x0 minus x star will survive, and xt minus x star will survive. Okay, so if we do that, then we have 1 by 2 gamma t. So we can separate out the 0 term first. Okay, so this is 1 by 2 gamma naught x naught minus x star plus, and so we have taken out the first term, and the remaining terms we can write like this. Yeah, the way we are doing is this following. So we take the first term out, and the remaining terms we have, which will be like, let us say t plus 1 minus t terms and so on. So let me write that. So this is plus half, and sum of t equals 0 to t minus 2. So 1 by gamma t plus 1 minus 1 by gamma t, and then ed of norm of x t plus 1 minus x star whole square expectation. So we have done a special arrangement here. We took the first term, and And then for the second term onwards, we have the indices from 0 to t minus 2, right? Yeah, so there is a reason for writing like this. So it's like we are preserving the first one, which is needed in the bound. In the bound, we see x naught minus x star is there, and the remaining terms are coupled together there, and then this 1 by gamma plus t plus 1 minus gamma t is bounded by some quantity here. Okay, so so yeah, we can do that. That's fine. So let us verify that this is correct. Okay, so if we sum from t equals to 0 to t minus 2, I mean t minus 1. So let us verify this. So if at t equals to 0, then 1 definitely I get the first term. Okay, so what remains is like t equals to 1 to t minus 1. All those sums are there or not, right? So t equals to 0, certainly this is there. T equals to 1, I will have 1 by 2 gamma t, gamma 1 basically, right? 1 by 2 gamma 1, but there 1 by 2 gamma 1 is there in the positive, and that is being reproduced there. And similarly, at 1 I have the one with the negative also, right? And these indices start from 0, right? So the way it is done is like you take out this term, and the sum will go here, and then you because you have taken out one of the term common, then you adjust for it here, okay, because this is the positive term here. So it's like you make this t plus 1, okay. So then you start producing this guy, and then the negative term is being produced by this, okay, and that's it. So okay, so I hope you are also convinced with this. It's a simple algebra only, but then you have to do this indexing correctly, okay. So now what we will do is that we will bound this, okay, and so this is also some inequality we are going to use. So this is 1 by gamma t plus 1 minus 1 by gamma t, and this is so gamma t we know, right? So gamma t is gamma by t plus 1, or square root of t plus 1. So we will substitute that. So this will be square root of t plus 1, okay, by basically minus of square root of t and by gamma. And this will be less than equal to 1 by square root of t, okay, or less than equal to 1 by 2 gamma square root of t, okay. So this I leave this as an exercise for you, should be okay, okay. So this is an inequality problem where you prove that a square root of t plus 1 minus square root of t is less than equal to half of square root of t, okay. So the hint could be that square root is a concave function, right? So that's the hint. Okay, so then we have this less than equal to 2 gamma square root t, so we will substitute it there, and then finally we will have, right, so we can also bound the term, also bound, so we will be left with this guy, right? But in the bounds we don't see terms with t, right? So we want to further kind of have a bound for these xt minus x star type terms. This is okay because this is something fixed. You started with initial guess, some solution is fixed, but you cannot keep these terms in the bound, right? So then we will try to replace that. So we are going to also bound the terms like expectation of xt plus 1 minus x star by using the fact that x star and the sequence xt belongs to the ball b0b, the center 0 and radius b. So again, boundedness of the solution will be used now, okay. So how it can be used is that we will look into this xt minus x star, okay. So it will be, we can extend this to xt plus 1 also. So let us see what these terms look like, xt minus x naught square. So if we do this expansion, then this is minus 2 or plus in this case. So it seems to be error there. So minus 2 xt x star and then plus norm x star, okay. So this is what we know, a plus a minus b whole square form. So what we know is that, so each of these are bounded, but then this negative term will create a problem for us. So I mean individually these are bounded because these are iterates of the PSST, and PSST bounds those by capital B. So this guy is bounded by B, and let us say B squared, and let us keep the, I mean, what will you do here? I mean cauchy squares I will apply, but then it doesn't get rid of the minus. You can make it plus because this is, but this is not negative less than, right? That's the problem. So it's still a problem. So this we have is, this is also bounded. So this I'm fine. But what we will do there, right? This was definitely negative. It's written positive. So Cauchy-Schwarz says that xt x star, okay, is less than equal to norm xt norm x star, and we are looking for upper bound, right? So if we do a negative, then we are in trouble. So this is less than equal to b squared, right? So this is what we have, and then the negative of this will be greater than equal to, so this will be greater than equal to negative of b squared. And then what do you suggest? Add. In the notes they just wrote it plus here. That itself is a, it's like not even, the starting point itself is a, so we are trying to fix this. Certainly it's not a plus, it's a minus, and we are certainly looking for differences, not the plus. So there is a typo for sure. And overall what they claim, maybe I will write this and you can maybe see if it is possible. So overall it's less than equal to 4b squared. If it was plus, then I can say that okay, it's possible, because plus 2b square will come from here, and then overall it will be less than equal to 4b square, because left hand side is a norm, so it's positive. So the right hand side, after expanding also I can take the mod, because it's a norm anyway. And if I take a mod, then I may apply a triangle inequality first. By triangle inequality, each of the terms will become positive, and then mod of this will be applied on this, and once the mod is applied, Cauchy-Schwarz does this, gives this. Okay, I hope what I'm saying, so I will write down this what I'm saying, and I hope we are not doing any silly mistakes. Okay, so what I'm saying is this, this can be written as a mod, because this is a square anyway, so this is a mod of this. Okay, so since this is a mod of this, so mod of x plus y plus z, all this, right, is less than equal to mod x plus mod y, like that. So that's the triangle inequality, right? So this is xt triangle inequality. So xt squared plus 2 mod xt x star plus a mod of norm, is just the norm itself, don't have to put mod there. So this way we can say, it seems okay. Okay, I hope I'm not doing anything silly here. So the and mod of this is xt x star is indeed less than equal to norm x norm y. So this is less than equal to b squared plus 2 norm, this is less than equal to norm xt and norm x star, right? So this is like norm xt norm x star, and this plus b squared. Okay, I hope I'm not doing anything. So this is like 4b squared. We can double check again later, but seems okay. Okay, are you convinced or not? So we have this bound 4b squared, and then yeah, so then we continue from here, which is the so basically we had a bound of this by this, right? And then now we also have a bound of this as a 4b squared. Okay, so these are the things we are going to use. So it's better to use that, and we can and we also have used one more. Okay, so square root of t minus 1 is less than equal to half. So 4b squared is that term, 4b squared by 2 gamma, that's fine. And then there was this last term that we missed, which is gamma t g squared by 2 here also, and this term was also summed, right? So this was sum of gamma t. So this was also summed, for all the terms were summed up, right? So this is t equals 0 to t minus 1. You have to do a couple of bounds. So So this is less than equal to, so I will write down and then we will dissect this. So this is less than equal to 4b squared by 2 gamma plus half of square root of 2 by gamma minus 1 by gamma 4b squared plus half 4b squared by 2 gamma square root of t equals 1 to t minus 2 and plus gamma g square by 2 and 1 by square root of t plus 1 t equals 0 to capital T minus 1. So this is being claimed. So let us see if it makes sense. And gamma t was gamma by square root t plus 1. X naught minus x star will also be less than equal to 4b squared. So here it's settled, right? So this is less than equal to 4b squared. This is also from xt minus x star. So this is less than equal to 4b squared by 2 gamma naught. So gamma naught was gamma by square root t plus 1. So t in this case is 0. So that's settled, okay. This term is indeed 4b squared by 2 gamma. And the second term is, so first of all, we have said that this term is less than equal to 1 by 2 gamma square root of t. So basically, we have summed over square root of 1 by square root of t. B square still remains for the second term, that's fine. So we are supposed to kind of fix this, okay, which may require some work. So let us see this term, right? So let's just focus on this. So 1 by gamma t plus 1 minus 1 by gamma t and e d of norm xt plus 1 minus x star. And this we know is less than equal to 4b squared. And this guy we know is less than equal to 1 by 2 gamma square root of t. And this is t equals 0 to t minus 2. Let us also put the half here. So this is less than equal to half and 1 by 2 gamma square root of t. So 1 by 2 gamma, only t will be remaining inside, okay. So 1 by 2 gamma and 1 by square root of t remains inside because it's the sum over t. And this is, and this guy is less than equal to 4b squared. So I can just write, n term comes, so you just separate out the 0 term, you're saying? Yes. Okay, I see. Okay, yeah, that seems. So we separate out the 0 term first, then we will have 1 by gamma 1 minus 1 by this, and so 1 by gamma 1 is square root 2 is there, right? Then square root 2 goes up, right? Yeah, so that's the first term. And from second term onwards, t equals 1 to, this is exactly what we have written, right? So let us do that. So instead of rubbing this, I will just write down the separate term here, and this is indeed correct from t equals to 1 to t minus 2 onwards. And the first term, we just have, we derive this, let's say. So t equals to 0, then we have 1 by gamma 1 minus 1 by gamma 0. So 1 by gamma 1 minus 1 by gamma 0, and half is there, and this guy is less than equal to b squared anyway, 4b squared. So half is there, less than equal to 4b squared, okay. So this is our second term, square root of 1 by gamma 1 minus 1 by gamma 0 less than equal to 4b squared is also there, and gamma t was gamma by square root of t plus 1. So gamma 1 will be gamma by square root of 2. So hence square root of 2 will go up, and then we will have gamma here, and this will be 1 by 1 minus 1 by gamma. So that's also okay. Okay, so this term, the terms that match, let us say we do like this, and then let us see the first term here. So 1 by 4 I see, 1 by 4 gamma actually I see, and 4b squared by square root of t also I see, and t equal 1 to t minus 2. So that's also settled, okay. So this term is also clear, okay. And then the remaining term is with the this, and that's should be the easiest one. So g square, yeah, that's the easiest one. You just substitute gamma t as gamma by square root 2 plus 1, and t term remains inside, everything goes out. So So that's fine. Okay. So then we can proceed from there, and this is further less than equal to. So it's like 4-5 lines left, maybe 10 minutes more. Okay. So this is further less than equal to okay, 3b square by gamma. So some b square that got cancelled, and b square by gamma I see. Okay, so let me write down, and it may be fun for you also to see how it came. So b squared by gamma and 1 by square root of t equals 1 to t, and then plus gamma g square by 2 and sum of 1 by square root of t equals 1 to t. Okay, so this is also algebraic thing, so you may try to see why it could be the case. Okay, so it's a simple tricks. Okay, so last term, okay, even the last term changed. We changed the indexing, so that's fine, but last term is change of indexing. Okay, so that you know, if you change the index from 0 to 1, so you have to do those adjustment. Square root t plus 1 becomes square root of t, so that's settled. Now see the other terms. So we added 2 more terms of the summations which were missing, you are saying, right? So here it's like t minus 1 term and t minus basically tth term, and we added those 2 as well, and then we also had to subtract those. Or no, we can just add it, right, if they're positive, because all those guys which we are adding are positive. B is positive, gamma is positive, t is positive, so we can add and still get away with the upper bound. Okay, or unless we subtract also, because I am also looking at this guy, because how come this guy got changed, right? So half is greater than root 2 minus 1, right? So we will put another half there, right? So it will be 1 by 4 gamma. So where do you trace this term? So 1 by 4, okay, the 4 with the 4b square got cancelled. 4 and 2, yeah, then how come 3 became?
b square by gamma.
Okay, okay, and then we have the remaining term, which is that b square by gamma term there, right? Okay, so let us do this. So yeah, we need further less than equal because of the fact this half is less than square root of 2 minus 1, so that we are going to use. So let us do that, and this we simplify. So this is 2b square by gamma and plus 1 by 4 of gamma, and then 4b squared, and 4 get cancelled, so we got the 1 b squared by gamma there, and then so we got 3b squared by gamma already. Okay, so 2b squared by gamma and 1b squared by gamma. So let us like cleanly kind of write this as 3b squared by gamma. Okay, it's in the video, so you can always trace this. So until here we have, and then the remaining term we have added, as you said. So we have added 2 more terms to make it go up to t. Okay, so maybe it's a good idea to show that here. So half of this is less than equal to half of t equals 1 to, now we added this in the sum itself, and then this is 4 b squared by 2 gamma square root of t. Okay, so so and then plus, and this term is like evident, so g squared by 2 1 by square root of t equals 1 to t. So we have added t minus 1 and t term, and those added terms are still positive, so it still keeps the upper bound. Added t minus 1, t minus 1 and t terms which are greater than equal to 0. So it seems like, yeah, it seems like we have everything. We exactly got what we were trying to derive, right? So that's it. Okay, so let us continue. So, and this is so basically now we see that these 2 sums in fact are match. Not just that, we will just do the sum of 1 by square root of t. So sum of 1 by square root of t, if we sum this, and then we will write the sum for that. So this will be 3b square by gamma, and then these sums are the same, sum of 1 by square root t, sum of square root t. So we will take that common, and that sum will be square root t minus 1. right? And then the common term gets added, the constants, the b square by gamma plus gamma g squared by 2. And then the summed up term is square root of t minus 1. Okay. So the sum of this, like you verify all this, right? So sum of t equal 1 to t, 1 by square root of t is square root of t minus 1. I mean, this comes from the integral bounds that we have used before as well. So the further hint, I think it worth giving here. So this is coming from the fact that 1 by square root of t is less than equal to s equals 1 to t, s minus half ds, which is 2 here. So ds 2 square root of t minus 1. You have used something similar before, but this again integral bound is being used here. And t range is, in our case, t equals to 1 to t. Integral bound gives us this bound. So so we use the fact that square root of t is greater than equal to 1. Okay. So if square root of t is greater than or equal to 1, and the note says cancelling the negative terms. So it seems like that minus term is there. Those terms will be forgotten. That seems to be the case. So if we drop the negative term, it will still remain greater than equal to. That's the point. Okay. And remaining, so let us do that. So this is another negative term, right? Because we will get something cancellation for this also. Okay. Yeah, you're right. So let us see this. So first, let us do that in a way that so b squared by gamma and 2. I could have just the positive term, like I keep it as a whole. Only the negative term I will try to split. So b square by gamma plus gamma g square by 2, and this is 2 square root of t, and the negative term is minus b square by gamma, and this is with the 2, and minus gamma g square by 2 times 2 again. Okay. So this we can clearly subtract from this, and this being a negative term, we will drop it and still keep an upper bound. So this is less than equal to b squared by gamma, and then we drop this, and what we have is this plus b squared by gamma plus gamma g squared by 2, and then 2 square. So square root of t is greater than equal to 1. So even we get rid of that, I believe. No, square root of t is kept. Yeah, we have square root of t here as a current step. So b square by gamma and 2b square by gamma plus 2 goes inside. Okay, 2 gets cancelled basically, and what we're left with is so we have inserted the 2 inside. So let's get rid of this, and then we put a 2 here. So b square by gamma and then 2b square by gamma plus gamma g square and then square root of t. That's it. And then now we will observe these 2 still remains an upper bound because it's greater than equal to 1, and then we take the square root of t common on the whole, and then we have 3b square by gamma as a final step, right? So we take this square root of t common, and then we multiply this. Basically, we multiply this by square root of t, so then we have 3b square by gamma plus gamma g squared. So now we are supposed to get this for the average. Okay. So what we will do is that we will divide by we will divide throughout by t. Okay. And then we will use Jensen's inequality. We have done these steps before as well. Whenever we have this average of the iterates, we do this. So let us do this as a final step, dividing throughout by and using Jensen's inequality. So if we do that, then as we have seen a couple of times, that this will lead to fx bar now. Okay, t minus fx star, and this is less than equal to 1 by t, and then sum of expectation of d and fxt minus fx star, and t equals 0 to capital T minus 1, and this is eventually less than equal to 3b squared by gamma plus gamma g squared, and then 1 by square root of t. Okay, this is what we have proved. So the average is less than equal to these iterates. Any iterates we have already this bound, so we have just put it there. Since we divided by square root of t, so that got cancelled, and denominator we have square root of t now. So I will stop, but these two references are there, which I'm not sure where. 42, 41, 42, and 41. These proofs are from there, so it's worth mentioning this. 42 is online convex programming by Zinkiewicz. Online convex. Online, do you know what is online? It's not like the internet one, okay? Online convex programming and generalized infinitesimal gradient ascent. So this proof was there. So International Conference Machine Learning Conference, ICML, and this is 2003. This is a bit older result. And 42 and 41 is stochastic gradient descent for non-smooth optimization, also in ICML. So these are like these proofs are picked up from there. Stochastic for non-smooth optimization. Well, this is ICML 2013. Yes, as I said, these algorithms are for machine learning. That's why these publications happen in there. Okay, but these are targeted towards these loss functions which have this behavior. So I believe that's it for today. Okay, so we'll continue again. Okay, thank you.